what can we do with it? Well, I've got an idea, and it involves some cockroaches. Well, just their legs, really. We can replicate one of Galvani's famous experiments using one of these guys. Hi, where are you? Come out. It's gonna be fun. Come do some science with us. Guys, one strong roach. Geez, this roach didn't skip leg day. Okay, I've got one of our roach friends, and I'm just gonna need its leg. So first, I'm gonna drop it in some ice water. This is gonna basically put the roach to sleep. You guys don't wanna see this. There, we'll dab them off. Not too wet. So we are gonna remove one of this cockroach's legs. But don't worry, they'll grow back. They're so small. And there we go. Oh, we got the leg. I'm gonna put this guy back with his friends. So I've got our cockroach leg here on our little platform. Grab a couple of these pins. One down here in the bottom part of the leg, one up here in the top part of the leg. Now we'll hook these cables up to our battery right here. Attach these to one of our wires over here. And when we touch the second wire to the pin, did you see that? The leg twitched. This is so cool. Voltage from our homemade battery is stimulating muscle activity inside of this cockroach leg because it's making nerves fire. If you thought that was cool, you can even do this with music because the signal coming through a headphone cable is basically just a voltage that speakers would turn into sound, but we can turn it into this. Look at that, the leg is twitching along to the beat. That's a sick beat, man. The voltage from our musical signal is stimulating that cockroach leg. This is incredible. We just replicated one of the very first experiments in all of neuroscience. Although, I don't think Galvani and Volta had hip hop, but anyway. Now let's do something different. Let's listen. Okay, now I'm going to plug these electrodes in to my special neuron detector box here. Flip it on. Now the signal you're hearing right now is mostly just background noise from the lights, from my computer plug-in, all this electric stuff around me. But watch what happens when I push on this roach's leg. There's no external electricity this time. There's no battery attached to this. This is electricity coming from inside of this leg. Now, how do neurons detect stronger signals versus weaker signals? Well, they actually do that by the rate at which they fire. The harder I push on this leg, the faster those spikes go. Bum, 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 bum. All right, I'm basically the most accomplished neuroscientist of the 1790s now. So Galvani and Volta got in this big fight. Galvani's all like, animals can make their own electricity. And Volta says, no, that's ridiculous. The salt inside the frog legs and the metals you touched them with created the electricity. And that's why the muscles switched. They were kind of both right, because outside electricity, like from a battery, does make nerves fire. But we do also have a form of electricity inside our bodies, in our nerves, just not in the way that Galvani thought. So how does that electricity inside our bodies happen? Well, first we need to get to know the hardware of your nervous system, the neuron. There are lots of different kinds of neurons, but they're all built pretty much the same. A cell body with the nucleus inside, and these things sticking off called dendrites, which are how neurons listen for messages from other neurons. This long part called an axon, which acts like a wire to send the signal from the listening end down here to this end. The synapse, the gap where one neuron can pass the signal to the next. Now, we don't find neurons in plants or fungi or anything else, only animals. In fact, all animals have neurons except sponges and whatever these are. And some of these neurons can be huge. I mean, the biggest animals are millions of times more massive than the smallest ones. The neurons running down a giraffe leg can be a few meters long. And there's one axon in a blue whale. Scientists think it could be the longest axon of any animal. A single cell more than 25 meters long. But there's another huge axon in this animal, the North Atlantic squid. It's like a millimeter in diameter, like 1,000 times the diameter of a human neuron. And this squid neuron is really important to the history of neuroscience because it let us figure out this. It's called the action potential. Action potentials are the zaps in our nerve cells, our living electricity. Now remember how I told you a battery makes electricity by separating charges and then letting them flow downhill? That's exactly what happens inside of a neuron. This is a cross-section of a neuron's axon. And there's this pump that connects the outside of the cell to the inside. And it's constantly pumping charged atoms or ions in and out like a revolving door. It's pumping positively charged sodium out of the cell and positively charged potassium into the cell. And outside of the cell are also all these negative chloride ions. And the inside of the cell, we find a ton of negatively charged molecules like proteins and stuff. So a neuron is like a banana in the ocean. It's full of potassium in this salty outside world. When you add all of these charges inside and out, a neuron, just sitting there, not doing anything, is negative inside. And thanks to huge neurons, like the one from that squid that we were talking about, scientists have been able to actually stick tiny wires in and measure that voltage difference. It's about minus 70 millivolts. So we have this separation of charges, like a battery. A neuron is more negative inside than outside. But we also have a chemical potential. Okay, what does that mean? Well, sodium wants its concentration to be the same on both sides of this wall. So sodium wants in. And potassium, it wants its concentration to be the same inside and out, so it wants to leak out of the cell. But the membrane doesn't let that happen, except there's these little doors in the wall. Some doors only let sodium through, some only let potassium through, and they only open if the voltage is just right. Now you're ready to see how an action potential works. Up here, a dendrite receives a little splash of a chemical from the neuron next door, and that signal says, let a little sodium in. And that ticks the voltage up just a tiny bit. Blip, signal, a little bit of sodium, blip, signal, a little bit of sodium. But if the cell body gets a big enough signal from its neighbor and the voltage hits this magical threshold, something incredible happens. All of these sodium-only doors suddenly open and positive sodium rushes in. And the voltage inside the cell shoots way up in like a millisecond. But then the sodium-only doors slam shut, and these potassium-only doors open. So potassium rushes out, so the voltage drops way down. And then the sodium-potassium revolving door pump chugs along and gets everything back to where we started, minus 70 millivolts. All of this happens in like 5 milliseconds. And one little action potential explosion leaks down the axon, boom, hits the threshold, sodium doors open, bam, they shut, potassium doors open, bam, they shut, and this explosion causes another action potential down and down the axon, a chain reaction of chemical electricity traveling from cell body to synapse. Whew. And at the synapse, a splash of chemicals released, sent over to the neuron next door, and the chain reaction goes on. All of these little living electrical messages happen in just a few thousandths of a second. When I tell my hand to move, it feels like that signal travels to my hand instantly. But not even light, the fastest signal in the universe, travels instantaneously. So how fast is a nervous system? Is it faster than a car? Faster than a plane? Faster than my phone? Well, ever noticed when you stub your toe, you can feel the impact almost instantaneously, but the pain takes a couple of seconds before you feel it? That's because these two signals, touch and pain, travel on two different types of nerve fiber with very different speeds. In your slower neurons, an action potential chain reaction can move down the axon between 1/2 and 2 meters per second, or around 4.5 miles per hour. But some nerves can speed up this chain reaction by being wider, the same way a wider pipe can let more water flow through, or by wrapping themselves in this insulation called myelin, kind of like insulation around a wire. That myelin around the axon lets an action potential chain reaction jump down an axon from node to node way faster. Incidentally, Nodes of Ranvier would make a great band name. Nodes of Ranvier. I don't know. We'll do something with that. In these insulated nerves, signals can travel down an axon at 80 to 120 meters per second. That's like 270 miles per hour. So depending on the neurons, the speed of thought can be a slow jog or a screaming race car. You're made up of dozens of different types of cells, from bones to skin to blood to spleen, whatever a spleen does, but neurons have to be the most amazing cells in your entire body. stretched like wires, and they can make their own electricity. They can transmit signals from head to toe in fractions of a second. And if you get enough of them together in one place and give them a few million years of evolution to wire themselves up, they can figure out the entire universe. They can even understand themselves. At least, I hope you do now. Stay curious. I know all these announcements after the video must get on your nerves,